Hello and welcome to this video where today we're looking at equations of motion, which is sometimes just known as SUVAT. So when we look at equations of motion, there are four different equations that we can use to work out, for example, displacement or velocities or accelerations or times. There are five symbols that we need to know about that are in these equations. The first one is S, which is just our displacement. So it's a vector, and it's basically the distance in a certain direction from a starting point. U is also a vector. That's our initial velocity. So that's the velocity that an object would start with. V is the final velocity. So that's the velocity that an object finishes with. A is acceleration, and T is the only object or the only quantity in here that's not a vector, because T is time. So let's have a really quick look at where these equations come from. So here we've got a velocity time graph, and we can see that this particular object is starting off at this velocity and it accelerates at a constant rate until it gets to this velocity, and it takes a time t to do it. So there are four equations that we can come up with. So our first one, if we start up here, if we were thinking about acceleration, we know that acceleration is equal to the change in velocity over the change in time. And if we think about how much our velocity is changed by, well, change in velocity, we take our final velocity and take away the starting velocity. So the final velocity was v, the starting velocity was u, so we have v minus u, and we divide it by t. So what we've got basically is we've got acceleration equals v minus u over t, and we can rearrange this to make v the subject, and if we do that, we get that the velocity equals u plus at. So what we've got is that we've got that our final velocity is equal to our starting velocity plus the product of the acceleration times by the time. And that is our first equation of motion. Our second equation of motion involves displacement. So we know, for example, if we want to know displacement S will basically be equal to the average velocity that this thing takes multiplied by the time. So if we've got the average velocity and we multiply it by the time, then that would give us the total displacement. Now the average velocity, this thing here, average velocity is equal to v plus u over t. So it's that value plus that value, and then we divide it by 2. So it's v plus u over 2. We divide it by 2, and that gives us our mean velocity. So if we take this and put it into here, we basically end up with s equals a half of v plus u times t. So if we want to know the displacement of an object, and we know the final velocity and starting velocity and how long it took to get from this velocity to this velocity, then we simply put our numbers into this equation. It'll tell us the displacement. So that is our second equation of motion. Our third equation of motion also involves displacement. So what we can do with this is, if we look at, let's start over here, otherwise we'll run out of room. Displacement for us, we're going to consider the area under here. Now you might wonder why we want a different equation for displacement when we've got this one. Well, this equation will have acceleration in it instead of one of the quantities in here. So if we know acceleration instead of, for example, the final velocity, then we can use this equation rather than this equation. So to work out the total displacement, that's the area under this graph, and I've split the graph up into two parts. This part here, this rectangle, and then this triangle here, because then it enables me to easily work out the area that's underneath this thing. So the total area is this rectangle, the area of the rectangle plus the area of the triangle. Now the area of the rectangle is simply t times u. So the displacement will be equal to, we'll write it as u plus u times t, because u times t gives us the area of the rectangle, plus this area over here, because the displacement is the total area. Now the area of this is, it's a triangle, so it's basically a half base times height, so is equal to a half. Well, the base is t multiplied by this distance up here. Now this distance up here is v minus u, like that. But we know from this equation up here, if we look at this equation up here and we rearrange it, v minus u is equal to at. So v minus u, I can substitute at into here. So if I do that, I get s equals, the ut is unchanged, plus a half of t multiplied by v minus u. But v minus u is at. So times at. And if I rearrange that, I end up with s equals ut plus a half at squared. And that there is our third equation of motion. Our final equation of motion we basically get from a mathematical way of deriving it. So we're going to start off with this equation here. So v is equal to u plus at. Now I'm going to square it. So that squared is equal to this squared. Sorry, u plus at all squared. And if we multiply that out, we get u squared plus 2 u a t plus a t all squared, so a squared t squared, like that. Now I can take out a common factor out of some of this, so v squared is equal to u squared plus, I'm going to take out a common factor of 2a, like this, and if I take out a common factor of 2a, I get ut plus a half a t squared, like that. But ut plus a half a t squared, so this whole thing in brackets is simply equal to the displacement. So I've got, finally, v squared is equal to u squared plus 2 as. So that is my fourth equation of motion. So that's basically where they come from. If we tidy it up very slightly, these are our four equations of motion. So these four are the things that we're going to, when it comes to looking at how, for example, velocity changes, or if we've got acceleration, we want to work out how long it takes for something to get from one speed to another, from one velocity to another, for example. These are the four equations that we're going to use. You get these in your data sheet. So these you get in your data sheet, so you don't really have to remember them. What is important, and this is incredibly important, this only works if you have uniform acceleration. In other words, the acceleration is constant. If it's not, you cannot use these equations at all. They just simply don't work, because then, for example, from our velocity time graph, this would be a curve and we'd be working out areas under curves and things. So these equations just do not work. They only work if your acceleration of an object is a constant value. So we're going to have a look at 3 different examples of how you would use this. And in order to answer these questions, it's basically a 3-step process. Now, because these things are vectors, what we have to do is decide a direction. So, for example, if we're throwing something up and down, we need to decide which way plus is and which way minus is. And it doesn't really matter which way we pick, so long as we remember which way is up and which way is plus and which way is minus. And that's simply because the S, U, V, and A are all vectors. So a direction upwards, for example, is completely different to the downwards direction. Once you've decided that, what I then recommend you do is you write down SUVAT like this, and you simply write down all of the information that you've got from your question. Once you've done that, there will be there will be 3 things that you know. There'll be 2 things that you don't. One of those things will be completely irrelevant, and the other thing will be the thing that you're trying to work out. So you pick the equation that's got the 4 things in that you need. So the 4 things you need are the thing that you're trying to calculate and the 3 other things that you know. And then you simply write that equation down, you put the numbers in that you've identified from here, and that'll give you your answer. So let's have a look how we do this. So this is a very simple example. We've got a stone and it's just simply, someone's holding it and then it's dropped off a cliff and it takes exactly 2 seconds to land. We want to know how high the cliff is. So what we've got is we've basically got this situation here. So this stone starts off here and it basically takes 2 seconds to hit the floor. So we're going to do exactly what I said. We're going to decide which way is which. So what I'm going to do is I'm going to decide that upwards is positive. I could say down is positive. It makes no difference. The answer I get will be exactly the same, but we'll just pick this. So then what I'm going to do is my second part. I'm going to write down every single thing that I know. So what do I know? Do I know the displacement? No. But actually, that's the thing I'm trying to work out. So put a little question mark. Do I know the initial velocity? Well, actually, yes, I do, because it's just dropped off a cliff. So it started from rest. So to start off with, its initial velocity is 0 meters per second. Do I know its final velocity? No, I'm not told that in the question. Do I really need to? Probably not. So that is the thing that I don't really need to know. Acceleration, because it's falling down, I definitely know the acceleration because it's falling under gravity. So that's 9.81 meters per second squared. And the time I'm given in the question is 2 seconds. So what I've got is I've got 3 things that I know. I know the initial velocity, the acceleration, the time, and I want to know the displacement. So I then go along and I have a look through the 4 equations that have got those 4 things in it. So one that doesn't have a v in it. And if I do that, I find this equation fits that. S equals ut plus half at squared. So it's got s in it, it's got u in it, it's got a t in it, and it's got an a in it, which 3 of those I know, 1 of them I don't. So now I simply put my numbers in, just being careful of what things are going up and what things are going down. So the s is the thing I want to find, is equal to 0, because that's my initial velocity multiplied by the time, like that, plus 1/2. Now, acceleration is downwards, and it's falling downwards with a magnitude of 9.81 meters per second squared. So it should actually this thing really should have a minus sign in front of it, because upwards is positive. So if this is acting downwards, this should have a minus sign in front of it. So this is actually minus 9.81 meters per second squared. And then I've got the time squared. So time squared will give me 4, because 2 times 2 is 4. And so if I simply do that on my calculator, then I end up with a final answer of minus 19.6 meters. So you might be wondering, why is this minus 19.6 meters? Well, it's minus 19.6 because it's in a direction downwards from where we started. So the minus is actually saying that we've finished up at a distance of 19.6 meters below where we started from. So that's because we defined plus to be upwards, so minus simply means that this is a distance downwards. So the second example we're going to look at is a similar type of example. This time we've got a stone that's thrown vertically off a cliff. So and we want to know what the displacement of the stone is after 2 seconds if A, we throw a stone upwards or with a certain velocity, or B, throw the stone downwards with a certain velocity. So what we've got this time, if we draw a picture, is here's our cliff. Someone's standing here and the stone is the same level as the cliff. In the first instance, we're going to throw the stone upwards with a certain initial velocity. And in the second situation, we're going to throw the stone downwards with a certain velocity. And what we want to know is what the displacement is after 2 seconds. So basically how far the stone is from its starting point after 2 seconds. So for part A, we're going to do exactly the same thing that we normally do. I'm going to, in both of these cases, I'm going to say that up is a positive thing. So going upwards is positive. And then I'm going to write down all of the things again that I know. So I've got SUVAT. So displacement is the thing that I really want to know. Initial velocity, this time, is 4 meters per second, so I know what that is, and we're throwing this thing upwards, so therefore actually it's plus 4 meters per second. The final velocity, it doesn't really matter what that's going to be, so I'll put that x. Again, acceleration is going to be downwards because the gravitational force is acting downwards, and the acceleration is again 9.81 meters per second squared, and the time again is equal to 2 seconds. So we've got a very similar situation to what we had before, apart from this time we're throwing the stone upwards or downwards. So again, if I do this, I end up with, I'm going to end up using exactly the same equation as we did before, which is S equals ut plus a half at squared. And again, I'm simply going to put my numbers in. So this time S equals u, well that's plus 4, multiplied by the time, which is 2 seconds, plus, so those two kind of go together, plus a half, and then the acceleration is minus 9.81 because it's acting downwards, multiplied by the time squared. Well, again, 2 squared is 4. And if I do that again on my calculator, I end up with an answer of minus 11.6 meters. So that's my answer. So basically what's happened is I've thrown this stone upwards, and it's gone upwards, and then it started to come back downwards, and it's got to, and after 2 seconds it's got to here. So my displacement is minus, because it's below where it started from, 11.6 meters. So that's part A. For part B, let's kind of draw some lines here so we don't get mixed up with what's going on. So that was part A. For part B, I'm going to do exactly the same thing. So I'm going to start off, I've got SUVAT again, so I write that down here. And it's basically the same thing. S is equal to something that I need to know. U this time is slightly different because it's equal to minus 4 meters per second. And the minus is simply because I'm throwing it downwards this time. Velocity, final velocity, it doesn't matter. A is minus 9.81 again, because it's the acceleration due to gravity downwards, and again the time is equal to 2 seconds. So again, you might well imagine we've got exactly the same quantities, we're going to use exactly the same equation. So S equals ut plus a half at squared, plus, I simply put my numbers in. So u is equal to, this time, minus 4 from here. That's equal to minus 4 times time, which was 2 again, plus 1/2, and again acceleration minus 9.81, put it in brackets so we don't get our minus signs mixed up, and again t squared, well 2 times 2 is 4. And again, if I do that on my calculator, so I've got minus 8 plus this thing, if I do that on my calculator I get minus 27.6 meters. So basically it's gone further, and you'd expect that because this time we've thrown it downwards rather than throwing it upwards. Okay, so our third example is slightly more difficult example. So what we've got is we've got a tennis ball that's been thrown upwards with an initial velocity of 10 meters per second from a height of 1.2 meters above ground level. We want to know how long after it's thrown does the ball reach a height of 5 meters above the point of projection. So basically what we've got is this. We've got the ground's here, a ball is starting off at a certain at 1.2 meters above it, and the ball is thrown upwards with a certain velocity. And what's going to happen is the ball's going to go up to the top of the flight, and then it's going to come back down again. So the important thing to realise here is if this thing goes up and then comes back down like this, there are going to be 2 times when it actually reaches 5 meters above the point of projection. So if that's 1.2 meters in total above the ground, it's going to be 6.2 meters above the ground, but it's going to be 5 meters above where it was thrown from. So there are 2 times, one on the way up and one on the way down. So what we're going to do is we're basically going to start off in exactly the same way we did before. And again, what I'm going to do is I'm going to define upwards to be positive. So, and then what I'm going to do is I'm going to write down my SUVAT, things that I know. So SUVAT equals like that. Okay, so displacement. Well, the displacement I'm going to start measuring from the point of projection. I'm not going to bother from the floor. I want to know if you want to know its displacement when it's basically the time of when it's 5 meters above the point of projection. I'm going to start measuring things from where it was thrown from. So my displacement is plus 5 meters, and it's plus because it's upwards. My initial velocity, it was also upwards, so my initial velocity is plus 10 meters per second. My velocity when it gets to 5 meters above here, again, I don't really need to know. My acceleration is downwards because the acceleration always acts downwards. So my acceleration is minus 9.81 meters per second squared. And my time is the thing that I don't know. So again, this is yet another example where we're going to use this equation. To be honest with you, most of the time this is the most important equation. There are obviously times when you don't use this equation, but in all three examples of this, we've used this equation. So S equals ut plus a half at squared. And we're just going to put our numbers in. So S is plus 5 is equal to u is 10. T is the thing that I'm trying to find out, plus a half times minus 9.81 times t squared. So what I've got is basically I've got a quadratic, so because I've got a t squared, a t, and then a quantity without t in it. So what I'm going to do is I'm going to rearrange this. Well, minus 9.81 is basically 4.905. So I'm going to take everything across to this side, so it gets rid of the negative sign from here. So if I do that, I get 4.905 t squared, and I'm going to keep quite a few significant figures because then I can round my answer up at the end. Minus 10t plus 5 equals 0. So now I've got a quadratic equation that I can solve. So I'm just going to use my quadratic formula. So t is equal to minus b, well, that's just plus 10, plus or minus the square root of b squared. Well, minus 10 times minus 10 is 100. Minus 4 times a, which is 4.905, times 4ac, so that's 5. And we're going to divide it all by 2a. Well, 2a is basically 9.81. And if I do the square root part on my calculator, basically what I'm going to end up with 10 plus or minus 1.38 over 9.81. And if I do that, I'm going to end up with two values. I end up with t equals 0.88 seconds, and I'm going to end up with t equals 1.16 seconds. Now both my times should be positive because time started at 0. And I suppose the really important thing, especially for mathematicians out there, is you can't really leave your answer as a fraction. You've got to make it into a decimal like this. So the two times when the displacement was equal to 5 meters was 0.88 seconds after it was initially thrown upwards, and 1.16 seconds when it was initially thrown upwards. So there are three examples, gradually getting more difficult. I would say that this part, in a sentence, is the most important. The equations you can get from your datasheet is actually how you do it that's really, really important. And if you follow this methodology, then it all kind of makes sense and you can't really go wrong. So that was Equations of Motion, or SUVAT. Thank you very much for watching, and I'll see you again soon.